In this tutorial, we'll take a look at a couple of factoring patterns. One's called factoring a perfect square trinomial, and the other is the difference of two squares. And this comes from what are called the special products, which are the opposite of each of these. Expanding and factoring are opposite operations. When we expand, for example, ax plus b squared, we get this a squared x squared plus 2abx plus b squared. So going from here to here is expanding, but if you're going from here to here, that's factoring. So that's what we're focusing on here. And the other special product, if we're multiplying two binomials, see here you're multiplying two binomials that are the same, you're squaring. Here we're multiplying two binomials the same, except one is a plus between the two terms in the binomial and the other one has the minus. Otherwise they're identical. And that factors into, or expands into a squared x squared minus b squared. So that's the two expanding patterns that we're going to use to factor. And I have several examples here, so let's start with the first one. So three terms, and it's likely to be a perfect square trinomial if something starts and begins with a perfect square. And the perfect squares, now for numbers, the perfect squares look like this. And I write the first several out. So for example, if I square 1, 1 squared is 1. That's the simplest perfect square. 2 squared is 4. 3 squared is 9. 4 squared is 16. If we square 5, we get 25, so 25 is a perfect square. 6 squared is 36. 7 squared is 49. May as well go to 100, I guess. 7 squared, so 8 squared is 64. If we square 9, 9 times 9 is 81. And 10 squared is 100. And of course, there are ones past 100, like 11 squared is 121. So those are the perfect squares. So when you see those for numbers, okay, that's a perfect square. But also, as soon as you see a variable with an even power, that's a perfect square. 4y squared, r to the 4th even power, w to the 8th, that's an even power. So those are perfect squares as well. So let's get rid of all that. So begins with a perfect square, ends with a perfect square. So it's likely that this is a perfect square trinomial. So if it is, you see what goes at the beginning here is what you square to give you y squared. What goes at the end is what you square to make 25. So that would have to be a 5, that would have to be a y. And then what you do is a check here. And this is kind of the shortcut for squaring a binomial. If I square y, I get the y squared. If I square 5, I get the 25. Now, if you multiply these together, see this 2abx? What the abx is the product of this first term and this second term in the binomial, and then you double it. So I go ax times b, which is abx, and I double it. The reason you double it is because we're squaring, there's two binomials. So if I multiply 5 by y, that's 5y. And if you double 5y, you get 10y. And that's and actually I'm checking my factoring by expanding. You can always check factoring by expanding. Y squared is y squared, 5 squared is 25, and y times 5y doubled is 10y. So that would have to factor into y plus 5 squared. Similar idea with b here. That's a perfect square. 9 was one of the ones I listed over here, and x squared, so even exponent, so that's a perfect square. Same with the 4y squared, that's a perfect square. So if it begins and ends with a perfect square, it's quite possibly a perfect square trinomial. So if it is, it would be, see, what we square to make 9x squared would have to be 3x. See, basically the square root of 9 is 3, and the square root of x squared is x. Square root of 4 is 2, square root of y squared is y. Or y squared is y squared, 2 squared is 4 if we go in the other direction. So this squared gives me that term, this squared gives me that term. Well, let's check the middle term here. If I multiply, let me get my pen going here. If I multiply these together, 3 times negative 2 is negative 6, and it'd be xy. And if you take that term and double it, you get exactly negative 12xy. So this certainly is the factored form of that, because I just expanded. this squared is 9x squared, that squared is 4y squared, and this times this doubled is negative 12xy. So that is the factored form of this. It is a perfect square trinomial. C, perfect square here. So 36 is a perfect square, even exponent on the m squared, so that's a perfect square. Same with the 49n squared. And so if it's a perfect square, it should look like this. It's 6m that you square to make 36m squared. It's 7n that you square to make 49n squared. 7 squared is 49n squared is n squared. And then we check the middle term here. So if we multiply these together, we would get negative 42mn. And if you double that, if you take that and multiply it by 2, you do exactly get this. So that is, again, a perfect square trinomial. Now, they're not all. Okay, so I do want to show you what happens in the next one here. Actually isn't a perfect square. You might think it is because it starts with a perfect square. The 9k squared is a perfect square, and it ends in a perfect square, the 4. But so we might think, well, it should be 3k plus 2 squared, because if I square 3k, I get this. If I square 2, I get 4. But if we go and check the middle term, so if we multiply this together, you see you get 6k. And then if you take that and multiply it by 2, well, we don't get 10k. That should be 12k if it was a perfect square. So that's why I've got this not equal sign here. So if I were to try to factor this, so I would use one of the other normal trinomial factoring, like the Australian method or decomposition. So I'm looking for two numbers that add to 10 and multiply to 36, because 4 times 9 is 36, and everything's positive, so I don't have to worry about any negatives. So 1 and 36 is possible, 2 and 18 multiply to 36, 3 and 12 multiply to 36, so to 4 and 9, and also 6 and 6. But none of these pairs add to 10. That adds to 37, that adds to 20, so quite a bit too big. That adds to 15, this adds to 13, and the smallest one adds to 12. So I can't get anything to make the 10k. So that's why we would say this trinomial cannot be factored, because you can't. There are no numbers that add to 10 and multiply to 36. They do not exist. So sometimes you can't factor them. That's why it says factor each of the following, comma, if possible. There are a few that might look like they're perfect squares or the difference of squares, and they aren't. So in E here, so it's called the difference of two squares, because y squared is a perfect square and 25 is a perfect square. It's 5 squared. So this would factor into y minus 5 and y plus 5. And again, that's the factoring, the second factoring pattern up here. See, this is a perfect square and this is a perfect square. So it factors into, you see, these two parts here are the same thing that multiply to give me the a squared x squared. And these two in the end are the same thing that multiply to give me the b squared in the end. Or actually, it's a negative b squared, because negative b times positive b is negative b squared. So I can check this by y times y is y squared. See, I need these exponents to both be 1, so that when I multiply them, they add to 2. And negative 5 times positive 5 is negative 25. See, there's no y term in the middle here. So it's not one of the perfect square trinomials. It's called the difference of two squares. This is the difference part, and these are the two perfect squares. So that's how that would factor. And remember, you can always check factoring by expanding. If I multiply these together, y times y is y squared. If I do this the long way, so that's y squared. And then this would be a 5y. And then this product is a negative 5y. And then this product of the last terms is minus 25. Now see, these are opposites, so they add to 0, so there's your y squared minus 25, like we started with. Okay, up at the top here, the top right, 49h squared minus 36r to the 4th, that's the difference. And this is a perfect square, and so is this. The 49 and 36 are two of the numbers I listed over here. Even power on the h, even power on the r, so they have to be perfect squares. So this should factor into, and you see what's at the beginning, The 7s are the numbers you square to make the 49. And if that's h squared, these have to be h's. One is a minus, one is a plus. And then what two things the same multiply to give me 36r to the 4th? So the two numbers that multiply to 36 are 6 and 6, or see, it's a negative, so I actually need a negative 6 for one and a positive 6 for the other. And these would have to be r to the power of 2, r squared, because remember, when you multiply powers with the same base, we add the exponents. 2 and 2 add to 4. So that's how that would factor. Similar idea with g, but they're not perfect squares first. But notice that there's a common factor of 2 here. So we can factor a 2 out of both of these. So if we do that, if we factor a 2 out, then 32 divided by 2 is 16, negative 18 divided by 2 is negative 9. So now it's the difference of two perfect squares. These are both perfect squares. So I would write out 2, and then what's at the beginning of each binomial are the two things the same that multiply to give me 16w to the 8th. So these numbers are 4 because that's actually the square root of 16. 4 times 4 is 16. And I need a w to the power of 4, so when I add this 4 and this 4, I get that 8 when I multiply powers of the same base. One is a minus, one is a plus. So if this is a 9, these need to be 3 and negative 3. And if that's a z squared, I need a z and a z here to make z squared when I multiply. So that's how that would factor. Always look for that common factor first. It doesn't exist in any of these over here, but that always makes any other factoring you do simpler. For h here, this is a perfect square, and this is a perfect square, but this is a sum. These were all differences of two squares. The sum of two squares doesn't factor. So we would say this binomial can't be factored because it's the sum, not the difference, of two squares. Last one here. And what I want to point out in the last example, and this again is a difference of two perfect squares. These are both perfect squares. Sometimes you can factor that, but then what's left can be factored again. And sometimes it can go 2 or 3 or 4 steps. So I'm going to start with this. It's, again, the difference of two perfect squares, even exponents here, 64 and 81 are perfect squares. So what goes at the beginning are the two terms the same that multiply to give me 64 w to the 8th. So 8 times 8 is 64, and if that's 8, these have to be 4s, the same number. I need a plus for one, a minus for the other, and actually, if it happens that you're going to factor this a second or a third or subsequent time, try to get in the habit of writing the plus one first. I didn't mention that up here. Actually, I wrote the minuses all first, and there's a reason for that. It makes the factoring a little bit neater. So this would have to be 8w to the 4th minus 9j squared. Remember, the same as this except with a minus. Now, this is the sum of two. These are perfect squares. This is the sum of two squares. That doesn't factor anymore, so I'm going to leave that one alone. We're going to just write that down again. But this is actually still the difference of two other perfect squares. So this actually can be factored again. So when you start with fairly large powers on your variables, that's when you can get into factoring it a second or third or fourth time or more if the exponents were big enough. So we're going to factor this again. So what goes at the beginning of each would have to be the two numbers I multiply together the same that give me 8 and then w to the 4th. So that would have to be w squared. This would have to be a 3. So there's the other factor. 3 times negative 3 is the negative 9. This has to be a j and a j to multiply to j squared. W squared times w squared, w to the 4th. So see, this one here factored again. It doesn't factor again because these are no longer squares. It's just a j here. Okay, so that would be completely factored. But it could be that these exponents would be high enough that, maybe this last one would even factor again if there happened to be like a 2 or another even number larger than that. So keep in mind that possibility. And that's the end of the tutorial.